Yeah,
Yeah,
I think it
started.
started now.
Yes. Yeah,
Okay,
Muna, you
today,
start.
yes. Okay, welcome back to lecture 14 on Riemannian symmetric space. Today, actually, I will cover some, today and day after the next lecture, I will cover some basic stuffs about Riemannian geometry, which will be required to study symmetric space. And for that reason, actually, I have in the WhatsApp group, actually, I have mentioned that it might be boring to some of you, but the aim of these two lectures is to put the things in better perspective. Okay, so so definition. So let A be an algebra over field K. A derivation D is a linear D is a linear map from A to A, so that d of UV U dot B is equal to U into dV plus du dot B. Okay, so UV belongs to A. Okay, so this is called actually Leibniz rule. Leibniz rule, and this simply means that derivation behaves like derivative. Okay, so now discussion. So let M be a subset of Rn. Okay, and we equip M with subspace topology. Suppose M is a smooth manifold. For instance, you can take, for example, you can take Sn, Hn. Okay. So, okay. So let P belongs to M. Let us draw a picture, something like this is suppose M, and this is my P. So let gamma minus epsilon to M be a smooth curve with gamma of 0 is equal to P. Okay, so now this gamma prime, you know that all of you know that this gamma prime 0 is called tangent vector of gamma at P belongs to at P. Okay. So this is our definition. So let us take this TPM. TPM is equal to, this is gamma prime 0. So that gamma is a smooth curve in M with gamma of 0 is equal to our P. Okay, and here actually you will it is understood that domain of gamma contains 0. Okay, 0 belongs to domain of gamma. So this TPM is called tangent space of M at P. And since really I am taking this gamma t, by definition it is belongs to Rn when you take derivative. So TPM is a subset of Rn. Okay, so TPM you can check that, it can be checked that TPM is a subspace of Rn with a dimension of TPM is equal to dimension of M. Okay, this is the left hand side is the dimension of the vector space and right hand side dimension of the manifold. Okay, so this is our this is our natural definition of the standard space. So as for example, you can first example, if you take this is Sn and you take P belongs to Sn, then you can take that TPSN is really this G belongs to this is inside Rn plus 1, right? P belongs to Rn, so that inner product of PB is 0. And this is our P perf. Okay. So second thing, you can do this exercise, and P belongs to this hyperbolic space Hn, and this is also we have seen that this is a subset of Rn plus 1. So TP of Hn is really V belongs to Rn plus 1, so that PV is equal to 0. And this is the corresponding bilinear pair. This is also P perf. Okay. So you can take this thing as exercise. So this is also okay. So the thing is, in mathematics, actually what happens that you really look the same thing in many different ways, and the purpose is to understand the things in a better way. Okay. So for instance, you can really consider this example. If you take any suitable measure, then you can really think of as a measure as a linear functional on some spaces. Okay. The same object and you are thinking in a different way. So we will do similar thing here. So we will really think the tangents, give an alternate definition of tangent space. Okay, I will describe everything, but without going into the deep of the theory. So let us see. Let U subset of Rn be open. Okay, all of you know that this is a smooth manifold, any open set, and let P belongs to U. Okay. So then TP of Rn is TP of U is equal to your Rn. So you can check that by your simple definition of tangent space. Okay. Now let V belongs to. Okay. So before that, let us see. Let C infinity P. This is really C infinity P is a set of. This is equal to set of all functions, all real valued function. Functions which are smooth in a neighborhood of P. This is my C infinity P. Now let V belongs to TPU. That means there exists a curve gamma with gamma 0 is equal to P and gamma prime 0 is equal to V. Okay. Now for each V belongs to TPU, I will define operator. So for okay, so I will define an operator d v comma p from C infinity P to R. Okay, by dvp of okay, this will take a function dvp of f is equal to this will be d by dt of t is equal to 0 f of gamma t. Okay. Okay, and actually this C infinity P is a vector space. This is a vector space. You can check that. So this is okay. So DBPF is not a. This is actually nothing but directional derivative of f of in the direction v at p. Okay. And you know that directional derivative only depends upon gamma prime 0. It doesn't really depend upon the curve gamma. So dvpa f is independent of the curve gamma. dvpf is independent of curve gamma. Sorry, curve gamma. So now the thing is, if you take let t is equal to t b, so you can say that. So then t satisfies the following properties. First is t is linear, so t of f af plus g is equal to a of tf plus tg. So this is a belongs to r and f comma g belongs to c infinity p. Second property is very interesting. So t of fg, so this is really fp and tg plus tf into g. This property you can verify by simply using this chain rule, so-called chain rule, and okay, so you verify this. Okay, so this is the exercise I am putting here. So here f and g belongs to same bit. Okay. So now let d1p, I will take d1p with the collection of all linear map S from C infinity P to infinity P to R. Okay, so that S satisfies 1 and 2. So let us write. So let d1p is the collection of linear map from C infinity P to R, so that so that S is linear and S satisfies 2. It means it is basically satisfy these two properties. Okay. So what I am getting, I am taking TPU. So I am getting TPU to a map some D1P. So I am, let us say theta is the map. So theta V, I am getting a map DV comma P. Okay. So it can be shown that theta D1P is a vector space.
Mona, is there any special reason that you're writing D1? Does this
Actually, I
one
am
mean
using.
something?
Actually, I am using this Algason's notation. D stands for derivation.
Yes, but is there any reason why you are writing 1? Just notation, right?
Okay, okay. I want to define this so-called PQ tensor later.
Achha.
This
Okay,
is
okay.
this 1 0 tensor.
Okay. Okay.
Okay, okay. Yeah, that's a good question. Can you show that D1P and is a vector space, and theta and theta from TPU to D1P is a linear isomorphism. So what I am doing, so that means TPU is isomorphic to D1P. Okay. So what we will do, we will identify this tangent space element with certain directional derivatives. Okay. So this is now onwards we will say that our tangent space is D1P. Okay. Now what I have done, I have really started a manifold M subset of Rn. Now I will really forget this thing. Okay. I will ignore this thing. I will just start from a manifold M, and then actually we define tangent space and vector fields, bagara bagara. So okay. So let so M be a smooth manifold. Okay, I am not assuming here that M is a subset of Rn plus 1. This is the important thing. So now let we define TPM is equal to, by definition, this is D1. Okay, so this is called tangent space of M at P. Okay, so at P. So D1P is the, by definition, tangent space is the collection of all linear maps from C infinity to P to R, so that it satisfies the second property, T of Fg is equal to Fp Tg plus Tfg. This is important. Now I will
These
define
maps
a
are
vector.
linear, means real linear, right?
Yes, real linear actually. I have. So, S is R linear. Okay, yeah, thanks. This is R linear. Okay, so okay, so this is the thing. Now let C infinitive is the set of all smooth function from M to F, function from M to R, so that F is smooth. This C infinitive is an algebra. Okay, so and C infinitive M is an algebra. Okay, you can multiply two function and add two function and also. Now the thing is we will put okay, put F is equal to C infinitive. This is just for notational convenience. Okay, so a vector field X, okay, is a mapping sorry, X from M to disjoint union of P belongs to M D1P. Okay, so that, okay, so first condition is XP. Okay, I am writing this P in the below. XP belongs to D1P. Okay. The second thing, for each P belongs to M, the map P going to this XP, let us write this in a different place. So for each F belongs to C infinitive M, the map P going to XPF is smooth from M to R. Look at the definition very carefully if you have not seen. A vector field X is a mapping X from M to this thing P belongs to M D1P, so that XP belongs to D1P. So that means XP is a tangent vector. And second thing is saying that for each A belongs to C infinitive M, P going to XPF is a smooth function from M to R. So what do you mean by vector field? This is just an assignment P going to SP, so that XP is a tangent vector, and second condition says that this assignment is smooth. Okay, so there is also a definition involving coordinate chart, but I am avoiding it. Okay, so this is the vector field. Now, so let F belongs to C infinity.
The union you wrote, that union is automatically disjoint, right?
Yeah, automatically disjoint, but I have written. That's all. Because it depends upon you. Let A belong to C infinity. So I define let X be a vector field. So we define this is really X F, okay, at some point P. Okay, so this is really XP of F. Okay, so that means now. So this is look at so this map. So if you take this thing, now you can check that X of AF plus G is equal to A of XF plus XG. This is A belongs to R. And second thing is since XP satisfies this condition 2, okay, so you can say that this will be something like X of FG is equal to XF into G plus F into X. So this F comma G belongs to C infinity. Okay, so this means that this implies X is a derivation of the algebra C infinity. Okay, so this is so now the thing is conversely one can check that any derivation of C infinity by n is a vector field. Okay, so let D1m be the collection of set of all vector fields on M, and this is nothing but set of all derivations of C infinity M. Okay, so this D1m is a set of all vector fields on M and set of all derivation of C infinity M. Now let F belongs to C infinity M. Okay, oh, C infinity M. So you check that as so check that xf also fx and x belongs to if x belongs to d1m, it is a vector field. Fx is also a vector field. What is the definition of fx? Fx of g by definition f into x. This is my definition. Okay. So that means d1m is an C infinity by m model because I can really multiply the function to a vector field. So d1m is a m model. You can check that. So and also if x belongs to d1m and y belongs to d1m, we define, okay, define xy is equal to this composition of xy minus yx. Okay. So check that this xy belongs to xy is also a vector field. Now, so it can be shown that D1M is a Lie algebra with a Lie bracket. This is this thing. Okay, so this is the thing. So D1M is a F module. Okay, so D1M is a F module, and recall where F is really significant. Now, if it is something is a module, then you can consider its dual, and that is also an F module by linear by abstract algebra. So let T small 1m be the dual of D1m. Okay. So precisely what D1m? D1m, this is the set of all T linear map from D1m to really here. This is I will take D1m to F, and so that T is F linear. This is not R linear because I am considering the dual of the F module. Okay. So now, so elements of D1M, elements of this D1M are called differential one forms. Differential one forms or simply one forms. Okay, simply one forms. Okay, sometimes you write this D1M in most of the book. People will use this notation. Instead of D1M, they will write chi m, and small d1m they will write this is omega 1m. So I will use the I may use this notation also. I do not know because it's very standard. So elements of d1m are called differential one form or simple one form. So by definition, d1m star is equal to your d1m, and this so and if you take this d1m star, this is d will be your d1m. If you are look for proof, see Helgason, or proof see Helgason or Kummeration, you can look at. See or Kummeration. Okay. So now this is the thing. Now we want to define something called tensor field of type R, S. Okay. A tensor field of type R, S on M is a F multilinear map T from, okay, I will take first D1M, D1M, D1M. This I will take, this is R times. Okay. Then I will take the other one, and superscript d1m, d1m. This I will take this is s times. Okay, so this is s times. Now take from this to f. So by definition, so this is a very important thing. So since I am using this d1m star is equal to d1m, using this thing, two things, one can say that a vector field is an 1-0 tensor. Is 1-0 tensor, and a one form is 0-1 tensor. Actually, people also include this thing, function spaces also as a tensor element, because we want really they want to consider this also called tensor algebra, and that is so. So any f belongs to C infinity to M is a 0-0 tensor. This is assumption. So 0-0 tensor means this is so DRSM. This is really set up all tensor T. So the T is a tensor field of type R, S on M. Okay. So one also sees that DRSM star is equal to DSRM. Okay. This is, you can look at this all everything what I am saying. You can look at Algason or accumulation. Okay. So this is a thing. Now I want to define something called smooth map, differential of a smooth map. So differential of a smooth map. Okay. So let M and N be two smooth manifolds. So you take this F from M to N be, so let F from N to N be smooth, and P belongs to M, say. So I want to define TFP, okay, from TPM to TPN. TFPN, not TFPN by. So DFP should will take a tangent vector from TPM. So this will be V belongs to TPM, and so this will DFPV is a really element of TFPN. So this, so I should take an element from phi belongs to symplectic FP by definition. So this will really phi. So this is really V of F composition phi. So this is really the thing that okay. So this is well defined. Okay, so let's say F is from M to N, and this is phi from N to R. Okay, so check that DFP is a linear map from TPM to TFPM. So now the thing is, if you have a map DFP from tangent space to tangent space, you can dualize that map, and you can get the transpose of that map from dual of TFPN to dual of TPM. So let F star. Actually, people write here lower star, but Helgason writes upper star. So like this, Helgason writes upper star, and actually I usually forget what is where to put the star. So I am writing now just uh, um, using the Helgason notation. So GPM star. So we defined by F star P. This will be sort of so omega, and omega belongs to TAPN star. So that will act on something. V belongs to TPM. So omega DFP V is just transpose of that. So V belongs to TPM and omega belongs to TFP N star. Okay. This is everything. Check that also. Check also that this so-called F star P is also linear map. So linear map. Now, okay. So now let F M to N be a smooth map. Okay. And let P belongs to M. So then F is called first concept. This is a very important concept. Immersion at P. Yeah. If DFP, this is a linear map, and this linear map is 1 1. Second thing is submersion at P. If DAP is on 2. Third thing is regular at P. If a DAP is 1 1 and not. So
So for the third case, like this M and N will have the same dimension, right?
So exercise in so in the first case immersion at P, then dimension of M has to be necessarily smaller than dimension of N. So in case I, this dimension of actually M is less than or equal to dimension of N. In case 2, dimension of N is greater than dimension of N. And in case 3, this is dimension of N is really equal to dimension. So these are okay. So now we want to really define something called submanifold, and this is a very important thing also. Submanifold. So let M be a smooth manifold. And then a pair N comma I, okay, is called a submanifold of M. Okay, if first thing is N is a smooth manifold. Okay, so this is same thing. Second thing is really I map. This is I map is 1 1. I is 1 1. third condition is for each P belongs to N. Okay. DIP is a map from where TPN to T of IPM, right? This is really immersion.
I is the inclusion map or what?
No, not I is a inclusion map. I is any map which is 1, 1. I am not assuming that N is a subset of M. Okay, I will tell about thing. Okay, so immersion map
from N to N.
where
Is a map from N to N.
oh I is 1, 1. Oh, sorry. Okay. Sorry, actually I should have mentioned this thing. Thanks. I from N to M is 1, 1. Sorry, that's okay. Okay, immersion. Now, if this I from N to In, this is really by definition it will be continuous. But if this map may not be a homeomorphism, so if N to In is a homeomorphism,
Isn't it a smooth map? This I, you are saying continuous.
by definition this is
By
smooth.
definition, it should be a smooth map, right?
Smooth map. This is continuous map, but but inverse may not be smooth. Inverse may not be even continuous. In this is actually subspace topology of M. So now if I from N to In is a homeomorphism, then Ni will be called an embedded submanifold of this. An embedded submanifold. Submanifold of N. Okay, so this actually this sometimes people call this as immerse submanifold, but whenever there is in book you find there is something is somewhere written this word submanifold, that means you will understand this the immerse submanifold. Okay. So if N is homeomorphic to In, then it is really called an embedded submanifold. Okay. For instance, you take just let us not go to that. So you can find an example like cumulation. You look at the cumulation. So this figure 8 actually you take something like okay. So let me try write in a different color. You will take this thing like something. Okay, figure 8 curve. This will be a immerse submanifold, not an embedded submanifold of R2. Okay, so this figure 8 curve will be a immerse submanifold. Submanifold of R2, but not embedded. You can look at the accumulation book.
But when you have that N is a subset of M, it will be always embedded, right?
No, that is not the case. Here it is a subset of this figure 8 curve that you are taking. This is a subset of R2. But why it is embedded? Because it is not embedded.
It is not a, but in that, see, it is the curve where it is intersecting, right? So
It is not intersecting.
it is not
Actually,
submanifold in the sense that at this point, at the point of intersection, it is not smooth, right?
No, it is not intersecting.
Or it is
It's
not
just
intersecting.
coming. Okay, this arrow is there, right? So it will not touch. Okay, that you will almost close the figure 8 curve, but it will not touch that. That's all. So these are very interesting. And thing is, Lie subgroup also. If you know That Lie subgroup, these are also emerged submanifold, not for the embedded submanifold. Okay, so this is a very thing. And so for instance, this Sn, example Sn, Hn, these are really embedded submanifold of Rn plus 1. Okay, so I have really defined about something submanifold. Okay, so what I am saying that we will identify n in with n with in, okay, and we will identify tpn with dip tpn, okay, and also we will borrow the topology of n to in. Okay, if I will do that, then we can regard n is a subset of m, and tpn is a subset of tpn, but there is a problem that but so topology of n need not be the subspace topology of n, because I am just borrowing the topology from in, okay, to in. Okay, so this is the thing actually you have to realize. For that reason, the Helgason starts from the beginning. He starts that n is a subset of n. Okay, so this is okay. This is how you have to really take this thing, and I want to really okay. So let gamma from minus epsilon to m be a smooth curve. Okay. So now the thing is, in the first setting, that I was really assuming that m is a subset of Rn. Then I take this gamma t. The gamma t is an element of Rn. Okay. So I was taking this differentiation gamma prime t, and this will lie inside Rn by your calculus. So then actually this was the tangent vector of gamma t at the point the gamma prime t belongs to, so t gamma t of m. This was my thing. Okay, when I started this thing, but I am ignoring this fact that m is a subset of Rn. So I want to really define gamma prime t in a different way. Okay, so let us define that. Okay, Riju, is this question is clear? Riju.
Yeah.
No, yes, Tapendu.
Yeah, Manav.
Yes, that gamma epsilon epsilon so a smooth curve. I want to define this gamma prime. Let okay, so what you do? Let u is equal to minus epsilon to epsilon. Okay, so let us say this is AB. You write A comma B. Okay, so let S belongs to U. Okay, now what a TSU really is a sub TSU is equal to R. Okay, this is one dimension. U is a subset of R, so TSU is equal to R. So I have really in TSU, I have shown you that this is identified with D1 of S. And what is the map? If you take alpha belongs to R, so this will go to some directional derivative, and there is only one coordinate here in AB. So that will be alpha. Suppose T is the coordinate, T is the variable. So alpha belongs to R, is equal to alpha d by dt t is equal to s. Okay. So TSU is your R. So I am taking alpha belongs to R, and I am identifying with a directional derivative, that is alpha d by dt of TS. Now I will define this gamma prime S. Okay. Gamma prime S. This is by definition d gamma. Okay. D gamma S. Okay. D by dt t is equal to S. By definition, d by dt t of this t belongs to S. This belongs to TSU. Okay. And this will become to T gamma S of M. Okay. So this is my definition. Okay. Now check that. So we have given this thing. Check that. One can check that with this definition, TPM is equal to gamma prime 0. So that gamma is a smooth curve in M with gamma 0 is equal to P. So now I want to give another description of this map DFP. So recall, let F M to M be a smooth map. So DFP is a map from TPM to really TFPN. Okay. So I want to describe this. I want to give another description of DFP. So, but I'll let B belongs to TPM. Okay. So that means if you have done this star, okay. So by star there exists gamma with gamma prime 0 is equal to V and gamma 0 is equal to P. So that means I want to describe this DFP of gamma. Now gamma is a curve from say minus epsilon to n, and this f is from m to n. So the f composition gamma is a curve in n. So this is simply f composition gamma prime 0. Okay. So yeah, so this is the thing. Now I can write that thing. Actually, this d by dt of f convolution gamma t. F convolution. This second this thing has no meaning, but meaning of that is this thing. D by dt of f composition gamma t is equal to f composition gamma prime 0. Rt is equal to 0, sorry. So dfp gamma is equal to f composition gamma prime 0. So that this is equal to d by dt of f composition gamma Rt is equal to 0. And this is another description of dfp. Okay. So this is also an important description. So this is okay. So now I really move towards Riemannian manifold or something. Okay. So I want to talk about Riemannian manifold. Riemannian manifold. So let M be a smooth manifold. A Riemannian metric G on M is a 0 to tensor. So that. So first is G is 0 to tensor, so it will take two vector fields in the argument. G of yx is equal to G of xy. G of xy is equal to G of yx. G of yx, and this is x comma y belongs to D1m. So second thing is for each p belongs to m. So GP will map from TPM to R. Okay, is positive definite. Okay, so what is the meaning of GP? GP, how does GP is defined? So GP of xp comma yp. Okay, so this is, see this, if x is a vector field, then xp is belongs to the tangent space, because by definition GP of xp yp is defined g of xy. G of xy is a function, and this is, so that means that is GP is actually a GP is an inner product on TPM. So this is a definition. Actually, I wanted to just write one thing. Hello, Manojda, are you there?
Yes.
Hello.
Yeah, I am here.
Is anybody there? Did I miss connection?
No, Nada, you are okay.
Yeah. Oh, okay. So actually, I have forgotten to write one thing. So let me write this thing. Actually, here actually. So this TPM actually, TPM is equal to really XP, collection of XP, where X belongs to, X is a vector field. This is the same thing. So I really, and how is XP defined? XP of F is defined by this XF of P. That F belongs to symmetry. Okay, so now coming by Riemannian metric G on M is a 0 to tensor. So that G of xy is equal to G of yx. And for HP belongs to M, this GP from TPM cross TPM to R is positive definite. And so that means GP is an inner product on TPM. So now suppose M is actually smooth manifold, and this Ni is a smooth Ni is a submanifold of N is a submanifold of M. Then what I am writing? I'm sorry, I am getting confused by myself. Sorry. I have defined this something called Riemannian metric. I should really define Riemannian manifold. Then actually, so Riemannian manifold M is a smooth connected manifold equipped with a Riemannian metric G. Okay. Okay, so connectedness I am throwing into the hypothesis. Okay, so let n be a submanifold of Riemannian manifold Mg, then this n, and if you restrict G to n, okay, so this is a Riemannian manifold. Okay, we will give various example of Riemannian manifold, but for the timing being, actually I will give just only one example. This is Rn. Okay, so if you take A belongs to C infinity by Rn, so that means it has really n coordinates. In Rn has n coordinates. So let u is equal to say u1, u2, un be the coordinates for u. So if I take this del by del ui, so this will be a vector field. Okay, so for 1 less than equal to 1 del by del y belongs to d1f. And what is the by definition this vector field? So del is a map from C infinity Rn to C infinity Rn. So this is the map C infinity Rn to C infinity Rn, and this will send f to simply del by del uif. Okay, so one can check that this d1m is really, this is really fi del by del ui, I is equal to 1 to m, so that fi is smooth. So this is really so smooth. Now let x belongs to your d1m and y belongs to also d1m. So this means implies that x is equal to some by I am using this, then d1m is this thing. X is equal to fi del by del ui, I is equal to 1 to n, and y is equal to I is equal to 1 to n g I del by del ui. So that means g of xy is equal to simply this is I is equal to 1 to n fi gi. Okay, and so this is actually, and gp is really your use. Okay, TP, what is TPM here? TPM is equal to Rn.
Del ui, these are only defined locally, right?
No, I am taking this Rn, right?
You are taking Rn?
M is, yeah.
Okay, m is Rn. Okay.
I have not really.
Oh,
Actually, I am sort of avoiding only giving the necessary definition. Okay. TPM is equal to Rn, and GP is the usual order inner product on Rn. Okay, but don't worry, we will see many examples of Riemannian metric, because symmetric spaces are special Riemannian metric. Part on Rn. Okay, so now, so this is the thing. Now let go gamma from AB to. So okay, so I will start. So let Mg be a Riemannian manifold. And Mg be a Riemannian manifold, and let gamma from AB to M be a smooth curve. So this is really, I define length of gamma. You define length of We define length of gamma. Okay, so length of gamma. So L gamma by this thing. This is a very important definition. AB. I take G gamma T gamma dot T to the power half root over and dt. And this is the same thing as this is analogous to the Euclidean case, norm of gamma T and dt. Okay. So now, so let P Q belongs to M. So I define D of P comma Q. I define this thing infimum of length of gamma P comma Q or infimum of gamma P comma Q is length of gamma P comma Q, where gamma P comma Q is a smooth curve joining P and Q.
Yeah, I may be wrong, but don't you need to take gamma to be piecewise smooth?
Actually, this is equivalent, but you don't need this.
You always
Because
get a smooth curve.
yeah, because connectedness and use that. This is a good question. This said actually
Because
if you take piecewise smooth, then there will be that will be good for that I would have taken.
no, just
So,
my only concern is that this existence of gamma given a tangent vector, there will be a gamma, but that will exist only locally, right?
locally, but really connectedness will help you to get a smooth curve and between joining P and Q. Okay, so let me put that exercise. Exercise. So that for any PQ belongs to M, there will always exist a smooth curve with the initial point P and final point Q. So to use use this fact that M is connected and M is locally invariant. M is connected and M is locally Euclidean. Okay, so now D is a distance function on M, and topology induced from the distance D will coincide with the original topology of M. So now I define one. Okay. So something called isometry. Okay. So let Mg and Ns be two Riemannian manifold. Okay. A map phi from M to N is called an isometry. geometry, if first thing is phi is a diffeomorphism. Phi, that means phi is 1 1 1 2 and smooth, and phi inverse is smooth. So that this means that is phi is 1 1 1 2 1 2, phi is smooth and phi inverse is smooth. And second thing is this is really G star phi star G is equal to H. Phi star H is equal to A. G. Okay, so I have not explained this thing, but what does that mean? So this means if you G is a matrix, G is a Riemannian matrix, and H is H of phi p of d phi p of V, d phi p of W is equal to G p of VW, or all VW belongs to your TPM, right? So this condition matters. Now HP really, that means d phi p. If you took two inner product space TPM and T phi p n, then this d phi p is a unitary map. Okay, so this is saying that. So now, okay, so let Mg and NH to be two Riemannian manifold. Riemannian manifold. So and phi from M to N is an isometry. Okay. So then it is easy to check that phi will preserve the distance. Take that dn phi p phi q is equal to dm p comma q. Okay. So this will follow from definition, but the converse is not trivial. The converse is also true. So I would like to like that theorem. So let G and NH be two Riemannian manifold, two manifolds. Okay, and let phi M to N be an onto map, so that dm of phi p phi q is equal to dm of p comma q. So only just phi preserves distance. That's all. No smoothness, no continuity assumed. So then phi is in isometry. Just only distribution in mass really thing. Okay, so here no continuity or no smoothness of phi is assumed. Smoothness of phi is assumed. Okay, so this is a very interesting theorem, and for proof you can see that you can see this book Kobayashi and Nomizu. But for Helgason, actually Helgason also has this theorem. Helgason assumes that M is equal to 1. So this Title is something called the foundation of differential geometry, and probably it is in volume 1 geometry. Now you can also look at Helgason, but Helgason assumes that M is under Helgason also. Okay. Now, so let okay, so let IM really is the map from phi M to M, so that phi is in isometry. So I have my previous result that IM is nothing but the distance between map from M to M, where I am assuming that M is in Riemannian manifold here. So check that. So IM is a group under composition. Actually, we will see later that it is a Lie group under composition. So now one thing. Okay, now next theorem is interesting. So let phi comma psi belongs to isometric group of M. So here as to assume let MG be a Riemannian manifold. Let phi and psi belong to IIM. We saw that. So phi p is equal to really phi p is equal to psi p, and d phi p is equal to d psi p at a given point p belongs to A. So then phi is equal to psi. So this is a very interesting theorem that this says that isometries are rigid, and in certain sense, to be precisely, isometries are determined by its value at a given point and its differential at a given point. And for proof, you can see Helgason. So I will leave this proof, see Helgason. So let us write that thing. Remark the previous theorem says that isometries are rigid. That is, an isometry is determined determined by its value and its differential at a given point. So okay, I will just define something called affine connection, then I will stop. Okay, so tomorrow we will continue. This is a very important concept, and tomorrow I will explain this. Something called affine connection, or sometimes this is called causal connection. Okay, so this is in fact the most important concept of so-called Riemannian geometry. So a map delta from D1M cross D1M to D1M is called an affine connection if so I should have write this. I will write delta xy. So I am not writing delta x comma y. I will write this if okay delta x okay y1 plus y2 is equal to, let us write this x y z. is equal to delta xy plus delta xz. So delta x of fy is equal to xf y plus f into delta xy. Third property is fx plus y z. This is f into delta xz plus delta yz. This is x comma y comma z. This belongs to d1n. So a map or delta is from d1 prime comes to dn is called an affine connection if it satisfies this property. Okay. Okay, so with this I would like to stop and I will be happy to answer any question. Mithunda, is there any question? Okay, tomorrow I will start this define exponential map Hopper-Rino theorem, and tomorrow I will finish everything about this so-called Riemannian geometry preliminary, and then we will calculate 2-3 isometries, and then we will go to symmetric sphere. Okay, so I will stop. So I will stop sharing the screen now. Yeah, tell me. Yes.
When you are defining Riemannian manifold on the definition,
Yes.
You open them.
Yeah. Yes.
Here. So we are saying that GP from TPM to TPM to R is positive definite. And we are defining GP equal to xp comma yp, g of x y comma p. So we know
Yes.
if x is a vector field, then xp belongs to TPM. But
Yes.
given a point in TPM, how we are going back to vector field, or am I making?
Yeah. This is the
wrong
thing actually I wrote you. TPM actually
Okay.
you can take that any vector field, any tangent vector is some xp. Actually, you can show that.
No, for a given xp, we are getting a vector field. Means how we are
if you given v belongs to TPM, so there will exist some x, okay, in vector field, so that xp is equal to v.
Yeah, that will always exist, but which x we are not saying anything about that. I mean, there will exist, but that will be unique.
That will not depend upon this choice of x. Okay.
Yeah.
So that this the calculation at the end will not really depend upon the choice of x. Actually, this thing will come and again. Tomorrow, actually, I will do something, and then it will be little clear. Actually, if you do not know this definition, what I am saying that you just look at this definition today. Okay, so very carefully.
Okay.
So will I stop sharing?
Yeah. And Munada, when you are going to the next page, could you be slow that means on the going to the next page? At that time, you are very fast.
Okay, you should have told me actually. Okay, in the class.
No, today I did that, but it will be good if on the next page.
Okay.
On the next page, it will be slow.
Thank you.
Thank you, Munada.